Right now, we've learned now that we learned how to compute the limit of sine of theta over theta. Theta approaches 0, then we can apply this to compute other limits, or what's known as changing variables. The observation is the following. So whenever you have, now that you know, sine theta over theta goes to 1, as theta goes to 0, then you know that any complex quantity here, like sine theta squared, for instance, over theta squared, goes also to 1 as theta goes to 0. Why? Because here, theta is a small quantity. So whenever theta is going to 0, theta squared is going to 0 as well. So you can write this as sine of y over y going to 1 as y goes to 0. What is y? Y is theta squared. And why do we know that y is going to 0? Because if theta is going to 0, then certainly theta squared is going to 0. So that allows us to conclude the sine of y over y is approaching 1 as well. The important thing to keep in mind here is that whatever is inside the sign has to be equal to what you're dividing by. So for instance, also example, this is the kind of mistake I want you to avoid. Suppose that you're asked to compute the limit of sine of 3x over x as x approaches 0. A lot of people write that this is equal to 1 because what's inside is approaching 0 and what's in the bottom is approaching 0, so by the previous theorem we know that that is approaching 1. This is, however, incorrect, completely incorrect. What I said is that we need to have the same thing inside the sign as in the denominator. So the correct way of going about this is to write this as the limit when x approaches 0 of sine of 3x, and we want to have the same thing in the denominator, so we write this as 3x as well. So now we have 3x in the top, inside the sign, and 3x in the bottom. But this is not what we had at the beginning, so we had x. So to make it equal to that, we'd multiply by 3. So the 3's here would cancel out, and we just get sine of 3x over x. But we want to write this as sine of 3x over 3x times something, because we know now that we can call this 3x y, say, lim of when y goes to 0, and we know now that if x goes to 0, then certainly 3 times x goes to 0 as well. Here y is equal to 3x. And now, well, this constant can be pulled outside. This is one of the first laws that we learned when we were computing limits. So this is 3 times the limit of sine of y over y approaches 0. But now we do know this limit, which is 1. So this whole thing becomes 3. Another mistake, common mistake to avoid, is the following. So let me pay attention to this. So sine is a very important. This is a very important remark, so that you avoid this other mistake. Sine of 3x over x is not equal to 3 sine x over x. So if you write this during an exam, it may give you the same final answer here. If you try to pull out the 3, it will give you that the limit is equal to 3. However, the reasoning is wrong, and this is not what we're evaluating, because you can simply guess the answer. What we want to evaluate here, we're looking for, is that you understand how to arrive at the conclusion, but not what the final answer is. So this is not equal to that. You cannot pull stuff from inside the sign. So this is not equal to that. So avoid this at all costs. you never put things inside either. So if you have a sine of x and you would want it to become sine of 3x, don't just, when you have a 3 that is multiplying outside, don't bring it inside. That's completely incorrect. So this will give you immediately 0 points. All right, so that that is the observation. So now let's move on to some examples. Some examples. So one is that the limit. So let's try to find out the limit at divided by the tangent of 7t as t goes to 0. So what is that equal to? Okay, so let's try to reduce everything. And so for the solution, what we do is we try to reduce everything to the limits we just computed, namely limits of sine of theta over theta, or 1 minus cosine theta over theta. So the first thing to do is to write the tangents here as the quotients of sines and cosines. So the numerator here is the sine of at divided by the cosine of at, and the denominator is the sine of 7t divided by the cosine of 7t. A simple rule how you work with fractions and how you perform these operations and turn this into a single fraction. We get that this is the same as the limit of sine of 8t divided by the sine of 7t times the cosine of 7t divided by the cosine of 8t. Remember here that we flip the fraction at the bottom and multiply the fraction at the top. That's how we obtain the thing, and then we arrange things and we arrive at this expression here. So what do we want? So now that we have this expression, well, this is the limit when t goes to 0. Limit, so we're computing the limit of this expression when t goes to 0. So we want to get a sine of at over, so what's inside the sine? Sine is evaluated at at, so we would like to divide by at as well. So what do? We divide by at, but then we need to multiply by at, because then if not, that wouldn't be equal to that. So we multiply by at, but then we have sine of 7t times cosine of 7t divided by cosine of 8t. We're gonna do everything here in detail, exaggerating everything, but only this one time. Then once you get how things work, you'll be able to replicate it, and you may skip the corresponding steps. We don't need to go over everything every time. So we have formed a sine of at over at, and now we will here we have 7t. So sine is evaluated at 7t, so we want to have a 7t on top instead. So we pull out this 8, then multiply by 7t, and sine of 7t, and then we need to divide by 7 to make these 7's cancel out. So cosine of 7t, cosine of 8t. And now we can write this using the law of the product and the law of quotient, and in fact we can also pull out this constant here, 8/7 outside, because it's a constant, so we can with 8/7 times this limit, but this is the limit of sine of at over at, all of that divided by the sine of 7t over 7t times cosine of 7t over the cosine of at. And now we can use the rule. So this is the limit of when t goes to 0 of 8/7, the limit when t goes to 0 of sine of at over at times the limit of the cosine of 7t over the cosine of at, t goes to 0, and then divided by this. Okay, so and why can we do that? Because all of these limits exist. Sine of 7t over 7t. Okay, and this is equal to 8/7. And the limit now of at over at, now we know that at is going to 0 when t goes to 0. We don't need to write that as the limit of sine of y over y. We know that at is some quantity that is approaching 0 as t approaches 0, and we're dividing by the exact same quantity, namely at, so that becomes 1. And the second expression here, let's notice that this quotient here is a continuous function at 0. So cosine so we just need to evaluate, which gives us 1/1. So times 1 over 1. And the denominator is also a known limit, so it's 7 sine of 7t over 7t as t approaches 0. And we know that if what we have inside the sine is the same as what we have in the bottom, and in this case, I mean 7t approaches 0 when t approaches 0, so and that's what we have inside the sine. And when we take the limit of that, and that becomes 1. All in all, our limit is equal to then 8/7. And that is one application. So another thing we can do, another example. So this example, we can call it example 1. Now we can go over another example here. Another example is a more direct one, sine of something like this. So you have sines, multiple sines multiplying and dividing and everything. And what is this limit equal to? To what? So again, the solution, for the solution, what we do is we write this limit, the limit that we want, as a product of and quotients of the limit of sine of something small over that something small over the same something. So what do? So here we start with sine, so we're gonna do it more streamlined this time. Sine of 3x, so we want to divide by 3x, then we multiply by 3x. Now we have times 1 over sine of 5x, so we want to have a 5x. Sine of 5x, and then we need to divide by 5x because it was not there before, and then we have the sine of 7x, sine of 7x, and we divide by 7x and we multiply by 7x, and then we have times 4x divided by sine of 4x, and we need to divide by 4x also. So all these things here are going to go to 1, because either we have theta over sine theta, or sine of theta over theta, where theta goes to 0. And for the rest, we'll see how that whole thing cancels out. So that's sine of 3x over 3x times 5x over sine of 5x times sine of 7x over 7x, 4x sine of 4x. And now we put together the 3x, the 1 over 5x, the 7x, and the 1 over 4x. You see here that we have an even number of x's in the top and the bottom. So, and they cancel out, so you have 2 x's coming from 3x and 7x, and 2 x's in the bottom coming from 5x and 4x. So they cancel out. We cancel this out, and this one, and this one, and we simply get a fraction like 3 over 5 times 7 over 4. And as I said, this goes to 1, this goes to 1, this goes to 1, this goes to 1. So what we're left with is simply this constant here. So 3 over 5 times 7 over 4. Okay, so I guess that's that explains how we proceed in general. So we just form everything we want, and then we put all the rest together, and we'll just get a bunch of constants, and that's how we compute these kinds of limits. Okay, now so example 3, we could be asked to compute the limit of 1 minus cosine of x divided by sine x. You can actually compute this limit using 2 techniques, but we might as well use the known limits that we just computed. So try to do that. Now that we're at it, let's try to do it using the known limit. So here, what do we know is that 1 minus cosine x over x goes to 0. So we want to divide by x, so as to form that thing. And then we need to multiply by x. Okay, and now these 2 limits exist, and we have a product of them. So what we want to compute is equal to that, and that is equal to the limit 1 minus cosine x over x as x approaches 0 times the limit of x over sine x as x approaches 0. And this is equal to, the first one is equal to 0, and the second one is equal to 1. Just in case, so let's make a small mark. In case it hasn't been clear, we've used repeatedly fact that the limit of, say, x over sine x as x approaches 0 is equal to 1. And in case it wasn't clear before, this is this is a consequence of the law of the product, so the product law, together with the fact that the limit of sine of x over x as x approaches 0 is equal to 1. How? Well, indeed, the limit of x over sine x as x approaches 0 is equal to the limit of x approaches 0 of 1 over, this is another way of writing the same fraction, 1 over sine of x over x. And this is the limit of 1 as x approaches 0 divided by the limit of sine x over x as x approaches 0. The limit of 1 is just 1, and the limit on the bottom is 1 because of this limit here, which is known. At least now we know that holds. So this limit here, when you flip it, you get 1 as well. So when you flip sine of x and x, you get the same limit. Okay, and so that is how you compute these kinds of limits, where you have like a sines and cosines of things inside. And next thing we'll do is we'll go over one final application of the squeeze theorem that comes up from time to time, and where everything that we've done so far doesn't apply. And you see why, and it's because of one of these situations where we don't have a limit for an expression involving sine or cosine, one where we expect to have a lot of oscillation. So that's what we're going to do next, and in the next video. So and that will conclude all. Basically, we'll cover all the applications of the squeeze theorem and the important applications to the computation of trigonometric limits.